Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about circuits that have an inductor in series with a resistor. Specifically, I want to look at the equations that govern these, or the basic equations that govern these circuits. And then in a separate video I'll delve into the graphs a bit that go with these time responses. So before we dive in too much, we might recall a few things that we've learned from previous lectures. Specifically, actually, the main thing to look back to is the RC circuits. So in some sense, like, you might want to go back and review all the stuff on RC circuits in general, but the particular points of RC circuits are that, okay, first of all, we combined two different circuit elements. And so how do we go about solving for the response? We had to use the Kirchhoff rules or laws, specifically the loop rule or the Kirchhoff voltage law, KVL, whatever you want to abbreviate that as, along with the known relationships between voltage and properties of the two elements. That is, for example, Ohm's law and the definition for capacitance. The other thing to sort of recall from these circuits is that they ended up having a response which was an exponential decay, such that, for example, the charge on the capacitor might be some maximum charge times e to the negative t over tau, or alternatively some maximum charge times 1 minus e to the negative t over tau. And note that both of those things are indeed exponential decays. It's just that one happens to be a downward decay and the other happens to be an upward decay. Finally, it's worth recalling that the constants in this equation, for example Q max and tau, end up being related to parameters within the circuit. Thus, tau was related to RC, and for that matter we could relate the half-life of decay to the tau. Tau is just the decay constant. So tau was equal to the half-life divided by the natural log of 2, for example. And we could continue recalling other points about the RC circuits, but I don't really want to do a long rehash of everything we did with RC circuits. Instead, I'd like to consider an LR circuit, so a circuit with an inductor and a resistor. So I have here the circuit diagram for a basic RL circuit. There's basically an EMF source present, or a battery present. There's a resistor, there's an inductor, and then we have a two-way switch. So in position, we call this position 1 and position 2. In position 1, the inductor and the resistor are in series with the battery or other EMF source. In position 2, they are not in series with the battery, but they are in a closed circuit. So let's apply the voltage rule or the loop rule, Kirchhoff voltage law, to each of these two possible switch positions. So in switch position 1, I have an EMF, I have a resistor, and I have an inductor. And so I should be able to write EMF minus the voltage drop across, or plus the voltage drop across the resistor, plus the voltage drop across the inductor is equal to 0. In position 2, I should just simply be able to write that the voltage drop across the resistor plus the voltage drop across the inductor is equal to 0. we have Ohm's law, which says that delta V for the resistor is current times resistance. Then we have the definition for self-inductance, which says that the induced EMF is negative of L times di by dt. So basically what we're using these two for is that this right here, Ohm's law gives me the voltages for V sub R. The EMF E sub L across the self-inductor gives me, in some sense, the voltage drop for the inductor in each of these equations. The last thing is that we have to kind of remember how current versus polarity works here. So if I was going to draw the current in this circuit, I would expect the current to look like this. And so what I end up getting is, after sort of substituting both of these equations in up here, is that the battery's EMF minus I times R minus L di by dt is equal to 0. And then likewise, if I move the switch to position 2, essentially what ends up happening is the current attempts to sort of continue flowing in this direction through the set, but that actually means that I end up with a current like this. So this would be I when in position 2. And so in some sense what that means is that I end up with IR minus L di dt is 0. So I basically have a pair of linear first order differential equations, just as I did with the RC circuits. That means that I'm going to have to solve these equations. Again, if I was going to comment on the type of equation, this bottom one is linear first order and homogeneous, and then the top one is linear first order and inhomogeneous, or non-homogeneous, depending on your preference, homogeneous, homogeneous, etc. So how you go about solving these is a little bit different. For the bottom one, it's fairly straightforward. So let's just do the bottom one, number 2. That one, if I rearrange the equation a bit so that I've isolated the differential part, I have di by dt is equal to, and then basically just rearrange everything else. So I have IR over L, or in other words, R over L times I. And so I'm basically looking for a equation I of t such that its derivative gives me back the negative of the equation. I left off a little minus sign up here, unfortunately, but should be the negative of the equation that I am looking for. So you can either guess at a solution, or you can look and see that things can be sort of split up, so that I have di over I is equal to negative R over L dt, and then basically just integrate both sides of this. And actually, if I put the integral so that I exclude constants, this is where the integral will end up being. And so on this side I have essentially like a 1 over x dx, and you know that the integral of that gives you the natural log. So I have the natural log of I is equal to negative R over L times t, plus some constant of integration, but that one ends up being 0 here. So now, to get rid of natural logs is sort of a recall that e to the ln x is equal to x, and ln of e to the x is also equal to x. So I should be able to take e to the power of both sides of this equation to get that I of t is equal to e to the power of r over L times t plus c. And then reminder that e to the x plus y is the same as e to the x, e to the y. So this plus c term actually is like an e to the c term. Since c is constant, e to the c is also some constant. Turns out that it is the initial value of the current. So I of t ends up equaling essentially I naught e to the negative r over L times t. And for what that's worth, this is also equal to I naught e to the negative t over tau, where tau is equal to L over R. So that sort of solves the condition 2 homogeneous equation version. The inhomogeneous version, for what it's worth, similar reasoning. To solve in position 1, you basically have to solve for the complementary homogeneous equation, which actually just is equation 2, hence why I did equation 2 first. So you get the same solution for that part, and then you have to also do a particular solution, which involves basically saying, suppose I of t is constant. So if you go back up here and you say, what if I is constant in this equation? Well, there does exist some value of I for which this equation could be valid, because this second term would be 0. In that case, I would just simply be given by epsilon over r. And as it turns out, that is also happens to be the maximum value of I that's consistent with the other two equations. So to get the full solution, you basically just add these two with an appropriate sort of constant. And that appropriate sort of constant is that this actually is negative. And so your full solution is I of t is equal to some I max, which is epsilon over r times 1 minus e to the negative t over tau. So again, this is the same as saying I maximum 1 minus e to the negative r over L times t, if we make all of our substitutions in. So that is your solution. And you can always double check my work on these even if you don't know differential equations by plugging the equations that I've obtained back into your original pair of green equations here, taking derivatives and seeing if you do in fact get 0 for them. As always, I would like to conclude this video with a short example. So we have here an RL circuit in which all the values of the EMF, the inductance, and the resistance are all labeled. We're told that there's no current initially flowing through the circuit, and that the switch is moved to position 1, which basically makes it R and L plus battery at time 0. And so we want to know 300 microseconds later, what will the voltage drop be across the resistor, and also what the current will be. So to solve this, we can basically make use of our sort of solutions to really equation or condition 1, which is the same as what we have here. And so we should be able to write that I of t is equal to some I maximum times 1 minus e to the negative t over tau, where the I maximum is given by the EMF divided by the resistance. So this actually will let us solve for the current. To get the voltage through the resistance, we could call that V sub R or delta V sub R of T. Well, that should just be I of T times R. And so given that Imax is epsilon over R, Imax is epsilon over R, and then we're multiplying by R, the R's cancel, so this just ends up being the EMF times 1 minus e to the negative t over tau. We see that in both cases it's useful to figure out what the value of tau is. So tau should be L divided by R, so L over R. Coming back over here, L is 8 millihenries, so 8.0 times 10 to the minus 3 henries. R is 24 ohms. That gives us about 3.3 repeating times 10 to the negative 4 seconds, or in other words, 333 microseconds. So we could write tau is 333 microseconds, approximately. Thus, it follows that the current at 300 microseconds is the maximum current. So that would be EMF over R times 1 minus e to the negative t over tau. That becomes 12 volts because our EMF was 12 volts divided by 24 ohms times 1 minus e to the negative, and then time was given as 300 microseconds. This right here is 333 microseconds. The reason why I'm putting it in microseconds is because if I have microseconds over microseconds, then the units sort of cancel. So that's kind of the right units. So we have 300 microseconds over 333 microseconds. So we're putting that into our calculator just to get the exponent terms, but this E term, if I were to put it in for e to the x, just to kind of save some keystrokes, I have minus 300 divided by 333. So this E term has a value of 0.4062 something. If I go 1 minus that same thing, I get 0.59. So this whole term in the parenthesis, 0.5937796. So I'll round it to 0.594. So I is going to be that times 0.5. So this is 0.2968. So 0.297 amps. And that is the current at that time. This part right here is 0.5 amps. So that's the current at that time. The voltage across the resistor at that time should be that current times the resistance, which is 24. So that gives me a voltage. So delta V sub R of T is I of T times R. And so that is about 0.297 amps times 24 ohms. And so what we end up getting is about 7.1255 volts. Properly speaking, I've given enough information here to probably have two significant figures. So probably this term here should have been rounded to 0.30 amps rather than 0.297 amps. So that's it. That's our example. And so hopefully I'm not really doing anything else in today's video. Maybe I'll put a little funny thing that I got when I was having to deal with signing in to make that circuit. Had this wonderful image captcha in which they asked where are all the buses, and then they gave me a reflection of a bus that I had to figure out. Turns out it didn't count for what it's worth. So bonus content, I guess. But the lecture's over. That's all. Hopefully you learned something from the lecture itself. And as always, thanks for watching.